So let's look at an example of Ghat in different types of patterns. So we'll see how Ghat behaves according to whether or not a pattern is a CSR process, whether it is a clustered process, or a dispersed or regular process. So I'll start by importing my libraries. So I need library SP for this, library spatstat, and spatstat being the new one that we're using now for spatial analysis of point patterns. And map tools. It has some conversion functions, and RGDAL to read and write data, like so. So I'll just run those just to make sure those all come out fine. I'm not missing any. Looks good. Just messages. Everything is fine. Okay, so we've loaded our libraries. So now I need to read in my data, and I have just put my data for this particular module or lecture just on my C drive. So I have my data here on C temp exercise 4. So that's where I'd put it, C temp, and then a lot of stuff in that temp drive. Should clean that up. Exercise 4, and there's the data geodatabase. So that'll be my path. So I'll just have the path here. So I'll say path, or I'll say GDB path. Equals, and then I'll just go up here and I'm going to go and copy that. And I'm going to use the what's called an R string literal now. So R, like that, and then quotes, and inside the quotes, parentheses, like that. And then in parentheses, I can just put in my Windows path as it is. I don't have to change any, I don't have to double the backslashes or change them to 4 slashes. So that's called an R string literal. So it can be handy in that it saves a little bit of time in having to deal with the different aspects of path statements in Windows. So remember, it's just R and then quote, parentheses, and then inside the parentheses, the path. So that'll be my GDB path. And then I'll read in, so I'll use my read OGR to read in a point layer. I'll just call it feature class points, PTS, equals read OGR. And then I have to put in, because I'm reading from a geodatabase, my GDB path. And then the name of the layer. And the name of this layer here is craters, for the Uganda craters. And then I'll make a poly, FC poly, read, OGR, GDB path, comma, and the name of this one is, okay, I can't remember. So what I'll do is I'll just say, here I'll say, just in the console OGR list layers, GDB path. There we go. So it lists all the layers in there. Volcanic field, that's what I wanted right here. So my second one is the volcanic field, which contains the craters. And so I'll read these in just to make sure everything works there. There we go. So we can see that we have read in now the craters, 141 features, and then the polygon. So I can just have a quick look at each of those, just so I can plot them as they are. I can say plot FC PTS, and it just shows the points. These are all the craters. And I'll plot the polygon, plot FC poly. And there's the polygon. So that's good. So my next step now is to put them together into a PPP object. And we can do that as long as both of these are SP objects to start with. So I'll say class FCPTS. So it's a spatial points data frame of package SP. And class FC_poly. And that again gives me an SP data type, which is a spatial polygons data frame. So now I'll just go over here to my script window, and I'll say FC_poly .owin equals, and that's just a variable, as .owin, and here I just have to put my polygon, FC_poly. Because remember, we need an owin object, which is the polygon or window, and we need point coordinates in order to make a PPP object. So then I'll say, for the next one, I'll just go Uganda.ppp equals as.ppp. I need my coordinates, which will be FCPTS at chords. So we need just XY coordinates and comma the name of the W, which is the parameter for the polygon that contains the points. And we call that here FC_poly .owin. So that's the owin object, and I'll just run that. And that looks good. So I'll plot that. I'll say plot Uganda.ppp. And there, just to make sure it's correct, it should plot the points as well as the polygon. I'll make it a little bit bigger so you can see it. So there's our Uganda polygon, the crater field, and then the craters as observed inside that polygon. So next, I can actually create Ghat. So here in my script window, I'll go back and I'll call this ug.ghat. That'll be the name of the variable to hold the Ghat function, again, which is the cumulative relative frequency distribution. So a cumulative relative frequency histogram. Another way of looking at the histogram, as we talked about in the lecture part for this. And this will be used gest, and all I have to put in here is a PPP object, Uganda.ppp, and then whether I want a correction. I don't want any edge corrections for this one, like so. And I'll just click, I'll run that. Then I can plot ug.ghat to have a look at it. So this is now our observed Ghat. So I'll say plot ug.ghat. And there we go. So again, what we see here is the expected value, which is the ... in red, so the dotted red line, and it says G sub Poisson at R. R is just the distance on the x-axis. Why do they call it R? Because R is a common one meaning radius for K functions, but it's just the autoplot function here for this particular package. Spatstat just puts R instead of D, but R means D. They're both measures of distance. And we see again that we have for almost the entire range of distances at which Ghat is evaluated, our observed Ghat line is below the expectation, which is the dotted red line. And so we have less points at any given distance than would be produced by chance, a CSR process, since a CSR process would be close to that black line. So that's our Ghat for our observed patterns in Uganda. So next, what we're going to do is make a clustered pattern inside of Uganda. So we can see what Ghat would look like if we had clusters of, very obvious clusters of craters. And for that, I'm going to use the RMAT clust. RMAT clust. Oh, I'm going to save that too. I'll just call it UG plus equals that RMAT cluster. And then what we need here is the first argument to RMAT cluster, and we can look at it here in the help file. So I'll put this RMAT plus like that, question mark, to bring it up. So what we see is RMAT cluster takes in kappa. Kappa is the intensity of the Poisson cluster's centers. It should be a single positive number, a function, or even a pixel image, which defines the probability surface. So for this intensity, I'm going to set it as the overall intensity of points within our study area. So 1 over the area. And I just found this one works good. 1 over area Uganda dot PPP window. And then I said that all, that all times 14. And that's because I played around with it till I got one that I liked in terms of a cluster process. And then I'll put the next one, which is the scale, 500. So that's the radius parameter of the clusters. So that's how big the clusters should approximately be. So I'm saying 500 meters, approximately. And then how many points per cluster do I want to generate? Approximately 10. And I want these to be generated within the Uganda polygon. So I'll say for the OWIN here would be the Uganda PPP $ window, like so. I'll put that on a couple lines so you can see the whole thing here. There we go. And I'll run that. And I'll do a plot. I'll say plot UG plus. And there we go. We see now within the Uganda polygon, we have very strongly clustered craters. So it looks very different from what it really looks like, but this is an example. So what would our Ghat now look like with this, as if these craters were the observed craters? So I'll make another Ghat. And I'll call the output UG plus dot Ghat, and that will be equal to GS. And in here, our PPP is UG plus, which is the clustered PPP process that is plotted right there. And then correction equals none, like so. I'll run that, and I'll plot it. OUG plus Ghat. There we go. Whoa. So we see a big difference here now. Again, the red line hasn't changed. The dotted red line is still the expected value for a CSR process. But when we have clustering present within our crater field, we see that Ghat rises very quickly to its maximum value. And Ghat is above, let's grab that little piece there. So what we can see here is that Ghat is always above the expectation. So all this area in here. So Ghat is above expectation for all distances. Therefore, we know then now what Ghat would look like for a clustered process. It would be above the expectation for a given distance. So for any distance, what it tells us, for example, here, if we look at just the distance of 500, we would expect around, let's say, 0.40%, I'll just do that multiplication in my head, 40% of the points should be at or below a separation distance of 500 meters in terms of their nearest neighbor distances under a CSR process. Whereas what we find up here is about 99%. It's not a very good 99, is it? 99%. So we have almost 100% of our points having nearest neighbor distances less than or equal to 500 meters when we have a clustered process. So that, in other words, we have more points at shorter distances of separation than a CSR process would produce. And that means clustering. And that's why we see that type of a plot in this case. So next, we'll look at creating a what's called a stratified random distribution, which will exhibit the type of regularity in a regular pattern without being a pure exact grid. So stratified random sampling basically takes, if I just plot Uganda PPP again, the way stratified random sampling works, and I'll just grab that. So to make a stratified random sample, we divide up the space into grid cells, however many you want, like so. And then within each grid cell, we randomly locate a point with equal probability. So one might be there, one might be here, one might be here, one might be here, 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 there, there, here, there, etc. And so what we end up having after that then is a repulsive or repulsed pattern, where we tend to find the points further apart than where we would find them in reality. So it creates a somewhat of a regularized pattern without being a pure absolute grid. And to do that, we can create, I'll call this UG, reg for regular, and that will be using the R strat function, RAT, okay? So the R strat will take in, again, our Uganda window, Uganda PPP, $window, and then the number of grid cells we want in X and Y. So I could say, for example, NX equals, because NX is the X, so it's thinner in X than it is in Y. So I'll have less, so I'll just have 10 going across the bottom and 30 up around along the Y-axis. So going back to our little diagram here, I've said to have 10 here, and then 30 up here. So I'll have 10 by 30 in terms of the grid. And then each cell will receive a point anywhere within within the cell with equal probability, keeping only those, of course, that are in the Uganda window. So there's the UG reg. I'll plot it. I'll just show, let's have a look at what that looks like. Plot UG reg. And there we go. Now we see something that has points. Sometimes they're somewhat close if they happen to be near the same portions of the cell, but you can see here there's very few that are you would consider as clusters with this random stratified pattern. So this is a regularized pattern, a repulsive that shows repulsion as a spatial interaction. And other points repulse each other. It's a type of interaction that's present there. So then I'll do a GEST of that. So I'll call it UG. Reg. Dot Ghat equals GEST. And then UG reg. And correction equals none. I'll run that, Control Enter, and then I'll plot it. So, okay, so now we see something which is the opposite of what we saw with the cluster process. So now, everything is below the expectation. Except when we get just up here, it was above a little bit, but that's inconsequential. So now the curve, so for a clustered, for a regular, I should say, or a repulsive interaction, so for a regular point pattern, PP, we find that for all, we'll say all for a given distance. A given just means any distance are randomly chosen on the axis here. So it could be any distance we're looking at. For any distance, the observed G hat is less than the expected. G hat. So for example, at 500 meters, we find in our observed pattern maybe about 5%. So 5% of the points have nearest neighbor distances less than or equal to 500 in our observed regular pattern, whereas that should be again around at 500 meters here, up there around 30, approximately 30%. So we should find approximately 30% in this pattern if it was a CSR process. So that means that for that to happen, we must have points that are further apart from each other than a CSR process would predict. So we can plot them all on one. And to plot multiple graphs, we have to create a graphical workspace that we divide. So I'm going to say here, I'm going to say win.graph equals, or win.graph, sorry, open and close parentheses. And I'll say the width of that, this is in inches, by the way. I'll say it's 8 inches by, let's say, height equals 4. And when I hit enter, you'll see a graphic pop up like looks like that. Now, when I plot, it'll plot here instead of in the R window down here. Then I have to use what's called par. Par is a control function for graphics outputs. And I want to say here, PTY, which is the shape of the plots, I want them to all be square. So the X and Y axes to go to 1 on each one, and or I should say the X and Y axes to be the same length physically. So you have a square plot. So I say S, and then I want to make a single row with 3 columns because I'm going to plot all 3 of them that we looked at are observed, random, are observed, regular, and clustered. So I use this parameter, mf row. I'm saying that equal to C, that has to be a vector, 1 row, comma, 3 columns. And then I'll say character size, CEX, character expansion equals 0.5. So that makes the font size half the regular font size. Like so. Now, I can just go back and plot. So I'll go back to my history here, and I'll find the first plot, which is just ug.ghat. And I'll hit enter. And we'll see it here. I'll just show you the plot as it's being built. That's 1. And it disappears underneath the window when I go back there. So I want to plot UG class on there. And I'll show you how it's being built. Oh, wrong one. So when I make a mistake like that, then I have to close the graphics. So I'll say graphics.off, and I'll go back and I'll run the win.graph again to make the graphic output, and then the par, like so. Then I have to replot. So I'll go back up here to, because I forgot the ghat on the first one. So I'll plot ug.ghat, like so. You can see it there. And then ugclus.ghat. You can see it there. And then down here to ugreg.ghat. There. So now I have all 3 plotted in the same window. So I can see them all at once. And I can expand that fully. And that gives me a better view then, a way to compare these things. So if we now look in comparison just visually, which one are observed? So this is the observed here, remember? I'll have to just grab that to bring it over. So that's our observed. That's the observed. This is the clustered. And this is the regular. Like so. So if we could try to look at which one our observed is more similar to, well, because it's below, everything is below the expectation, it's more similar to this over here. And that means we have something that tends towards a regular pattern of craters in the volcanic field. So there's some process at play that is tending or forcing craters to be further apart than just random, a set of random craters would indicate. So it generates a hypothesis now. So now we have a hypothesis we can test to see whether or not there's this observed differences here are statistically significant. We won't be doing that yet, but this is how we generate hypotheses, for example, to test that type of a question. And we can see very easily that our observed is not similar at all to this one. No, it's more similar to that one there, the check mark. And we could also go back, we could generate just a random pattern in there if we wanted to. But well, we don't need to because we have the expectation there, which is the red line itself. So that's the experiment. And we can learn a lot by always testing our measures, our statistics or econometric measures that we have, these spatial statistical measures, by looking at how those measures behave with extreme examples, like we saw here. We generated 2 extreme examples, one which is a very clustered pattern and one which is very regular. And by knowing how the extremes behave, we can then see where our observed fits in. Does it fit in more towards the regular behavior or more towards the clustered behavior of Ghat? And that can then generate hypotheses we can test.